Good afternoon, everyone. Welcome to another IDSS Distinguished Seminar. It's a great pleasure and honor to introduce Professor Sanjeev Arora from Princeton. Sanjeev is Charles Fitzmaurice Professor of Computer Science at Princeton. He's worked on theoretical computer science and theoretical machine learning problems. Is quite well known in both communities. He's won a series of awards, including the Packard Fellowship, the Godel Prize, Simon's Investigator Award. He's a member of National Academy of Sciences, and we're honored to have him today. Tell us about you for representation. Thank you, sir.
So this is joint work with an amazing group of young grad students, and actually one undergrad. Rishi Parker, who's an undergrad, Misha Kodak, grad student at CMU, former Princeton undergrad, Orestes Stavrakis, and I want to start by first saying what talk I'm not giving today. There are various talks out there. What is machine learning, the math of machine learning and deep learning, to a theoretical understanding of deep learning. I gave some of these talks, including in Cambridge, like at Harvard in the fall. So I wanted to give a new talk. And besides, these talks are on YouTube. So if you are interested in learning more about that branch of work, you can look it up there. So indeed, instead, what I'm talking about today is this. So broadly, I mean, I'll specialize to a specific question, but the broad issue I'm interested in is this phenomenon. Why does learning to do A help you do B later on? Now, this is completely an obvious thing, right? Of course, everything you learn up to this point will help you do whatever you're doing next. It's completely obvious, right? So, but like, for example, you major in math at MIT, maybe get a PhD even, and somehow, at some point, you go to Wall Street, and somehow that skill somehow helps you. But why? And again, this, as I said, these are like obvious things, right? Like, of course, what is the question? And the reason this is not obvious is that this is hard to capture for machine learning theory. The formal frameworks we have for machine learning theory, as we'll see, this is hard to capture, except if you go hardcore full Bayesian. Then there's no mystery ever in the world. You have some distribution in your head, prior and all that, over everything in the world. Everything is connected. You get new information. Your posterior gets updated. So there's no mystery ever. But then, even so, I mean, so firstly, I don't want to go full Bayesian because it's not clear you can do that kind of modeling and inference. And even if you could, it's not quite clear how to interpret the phenomena we'll see in the next few slides. So that's why I'm calling it a mystery. So talk overview. I'll specialize this question, task A and task B, to something called representation learning, which I'll describe. And we'll talk about the desired goals for this and need for the new theoretical framework. Part 2 is to give you background on this area, which I love, and I think there are people here who love, representations and embeddings. This is a very popular area in machine learning today, inspired by deep learning, but not necessarily only that. And so I'll give you some bird's eye view of why this is amazing or intriguing. And then the part 3 will be our new framework that I'm proposing, which is minimalistic, but still surprisingly powerful. And part 4 is a brief description of some experiments, which basically just illustrate the theory. There's interesting experiments already known in part 2, which I'll describe. And part 4 experiments are just to illustrate and support the theory. So part 1, representation learning and its goals, and why we need some new theoretical framework. And this is an instantiation of this phenomenon of solving task A is helpful in later doing task B. So what's a representation? So it's a way to represent your data in a different way, a different, more intuitive way. So data comes in, x, you apply a function on it, the representation function, you get f of x. That's the representation. Why have a representation? You have images already, that's in pixel level data or whatever, text. Why have a new representation? It's because you want to solve other tasks using these representations. So now, of course, if f is the identity function, you have preserved all the information of x. So of course, whatever you could do with x, then you could do with f of x. So we'll see what else you need. But anyway, these representations are called embeddings. Okay, these functions are called embeddings. They embed an object like image or text into a new vector. And of course, if you think about it at a neuronal level or neuroscience level, yeah, even the pattern of visual cortex activations generated by the image when it's flashed on our retina, you can think of that as a representation, which the rest of the brain is going to use to do something else. So this notion is ubiquitous. I mean, it's obvious that, yeah, any processing of x, you can think of it as a representation. So what people want in practice is powerful data representations. So for example, you want new classification tasks. So just to make it more specific and concrete, you want to solve now classification tasks. So you're given label data, in this case binary data in that picture, and you want to solve those classification tasks very well using a linear classifier. Now, of course, all of you know that these days linear classifiers have been replaced by much more complicated things like 100-layer deep nets. So the power of the representation is that instead of needing a very complicated model, you may be able to do it with a simpler model, a linear classifier, and potentially with less data, less labeled data. So if somehow you have a magical representation function, you can save on computation and sample a number of samples required. So you can, in this setting, you can think of the representation as a method that brings the semantic content of x to the surface. And this process of extracting out the semantic content of any image, any data point x is, of course, it applies to all of machine learning. I mean, in that sense, it's something that should obviously have implications for all kinds of other things. And indeed, people are very interested in this. A classic example, if you're machine learning, if you've done undergrad machine learning, is kernel SVMs, where you lift the data to a kernel representation and then classify using a linear classifier. This is just for illustration in case you've seen it. If you haven't seen it, don't worry about it. We won't need it. Any questions so far? Okay, so here's a, whoops, forgot to do some animation here, but okay. So ignore the tie and the beaver, sorry. With lots of labeled data, so there's just a deep net there, okay? Ignore the beaver. With lots of labeled data, deep nets learn powerful representations in the sense that I described. So here you have VGG19, which is a 16-layer deep net. And it's trained on labeled data ImageNet, which has 1,000 classes with 1,000 examples each, so 1 million examples total labeled. It took a lot of effort to create that labeled data set. It was actually created at Princeton. So you train this net using this labeled data in the standard way, backpropagation, all of that. And it does well, as you all know, like these days, these kinds of nets are exceeding human capabilities on image classification. Now, here's the point. The classification accuracy would be abysmal if you only had 2 classes. Right? So this net, after you train with all the classes, also if you are only interested in 2 classes, dogs versus cats, it does very well. But if you just gave it the 2-class data, the performance would be abysmal. So in other words, the data from the other 998 classes, even though it's not relevant to those two classes, classifying those two classes, is somehow important for learning the right representation, the rest of the deep net. Okay? And furthermore, so it intuitively is learning the right representation, but actually, even in practice, you can take the vector on the penultimate layer or the last two layers from the end or something, take that representation. So the image is passed through the deep net to that last layer, or the last but one layer. And that representation can be used as a powerful representation in all kinds of other tasks. And this has revolutionized computer vision, this kind of idea. So if you want to now do passenger detection in the image, pedestrian detection in the image for your self-driving car, you can use these kinds of representations. Okay, so this vector on the penultimate layer is useful, and it's a powerful representation. And now you're allowed to look at that line and the beaver. So that beaver, suppose, cuts off this last layer, and that's the output of the net now. It's not a label, but this representation. And I call it the headless, well-trained deep net. Okay? Just to make it stick in your memory from now on. Okay? This is viewed in the field as some kind of a gold standard representation. Okay? So I want you to stick with this image, the headless, well-trained deep net, because that's sort of that's an amazing product of deep learning. It's trained using lots of label data, and the whole question is that we want to learn similar quality or very high quality representations using unlabeled data. Okay. By the way, the original graphic I had was a little bit more bloody, and you know how it is. I remember this stage as a student. My students were like too embarrassed. Like, what? So they convinced me to change it to something more. Okay, sorry. Ignore that. Yeah, this. Yeah. Okay. And so, like, one notion of powerful data representation that's used in the field is to compare it to this headless, well-trained deep net. Okay, that's actually the way people say test the quality. The headless deep net on images can do this well on the downstream tasks, some suite of downstream tasks. And now if you have another method to train representations, we're going to compare them to the headless, well-trained deep net. That's the way people are doing this, one way. So that's what like a good theory would tell us. Take some representation function, like some way to train representation functions, and sort of give some performance guarantees for that representation. That's what we would like theory to do. Okay. Now, the reason that's not clear at all in the standard machine learning paradigm, if you remember even the basic machine learning you've been told, the standard paradigm to which theory applies is that you train the learner on some data, and you test on some held out data, either held out data or think of it as testing on the entire distribution of data. And training and test involve the same objective and involve IID samples from the same distribution. That is the canonical setup in machine learning theory. And then training loss minus test loss is generalization error. And trivially, for a fixed model, the right-hand side goes to 0 as the number of training samples goes to infinity. And the generalization theory is like trying to derive bounds for how many samples you need, et cetera. But the point is, training and test involve the same objective, the same task, and involve IID samples from the same distribution. But here, test and train involve different objectives. You train the representation somehow. I haven't even talked about it. We'll see in a couple of slides, various methods. And we didn't know the test tasks while training. It's like they are given to us later. So training didn't know about the future tasks that representation will be used on. So it falls squarely in that open problem that I talked about. Training on task A, testing on task B. Any questions? Okay, just past work. There's a lot of theory on semi-supervised methods where often training uses unlabeled data as well as labeled data from the downstream task. So there isn't a lot of data from the downstream task, but you have some of it while training. So that guides you in your choice of representation function. So that's semi-supervised methods, and those have been around for quite a while. And as I said, there's a generator model. So the full Bayesian model would be like everything is connected to everything. But there are also generator models, topic models, language models, variational autoencoders, et cetera. These are trained, again, where training and test objective are the same. So the perplexity kind of objectives, log likelihood. If you don't know about these, don't worry about them. Unclear why these kinds of objectives should suffice for representational learning. You are sort of fitting a probabilistic model to data. Why should that let you do representational learning? Somehow that's a question, even people who do it all the time don't have a good answer for me whenever I ask them. And Andre here, when he was a grad student, and I were thinking about this, and we sort of wrote up some critique of that view on my blog. And here's the final reason why generator models really aren't completely satisfying, because we'll see that the methods, not the above methods, but the methods we'll see in the next slide, do not appear to do Bayesian reasoning, at least in any obvious way. So that's why I think we need some new theory. All right, so now part 2, the lore of semantic embeddings. Fascinating topic, these semantic embeddings. And let's see some examples. So the simplest example that got me hooked into this area some years ago was word embeddings. And you learn, so these are embeddings, so a vector representation of the meaning of a word, of the semantic content of a word. And they're learned via language models, probabilistic models of language. And the idea is to use a large text corpus like Wikipedia, billions of words, to train a model to predict part of the text from adjacent text. So sort of completing the blanks, filling out the blanks. So I went to a cafe and ordered a blank. And it could be, the correct completions could be coffee or croissant. And a puppy would be a ridiculous completion or low probability completion. So clearly, if you can train a model to do this, it should implicitly pick up on grammar rules, common sense, et cetera, right? That's intuitively clear, but actually turns out even very simple models, capture the meaning of words very nicely. So the concrete model I have in mind is Word2Vec, or a baby version of it, a famous model, which wasn't the first language model, nor the last. It's just a very popular and simple model. So it does the following. The parameters of this model is a vector embedding for each word. It's trying to learn that embedding. And it's trained on the following task. Using the preceding 5 words, W1 through W5, is outputting a distribution on all English words. And the functional form for the distribution is something very simple. It's that the probability that the next word is W, given the last 5 words, is proportional to the average inner product of its embedding with the embeddings of the previous 5 words. And there's an implicit normalizing terms in these kinds of exponential models, which I'm ignoring in this exposition. And so now this model is trained by maximizing the probability assigned by the model to Wikipedia, the full corpus with 1 billion+ words. So the loss function is a reciprocal of the probability. And that you can factor out using Bayes' rule in this kind of expression, which is an analytic expression of the word embeddings. And now you train it using some kind of gradient descent. Okay, I'm being very, very superficial with this description. And the concrete training method that is used is something called negative sampling. And if you examine what it does, it's trying to do the following task. In the entire Wikipedia, words that tend to co-occur get vectors with high inner product, and random pairs of words, which presumably don't co-occur together very much, get low inner product. Okay. Now this Word2Vec algorithm is very popular, I know, so I'm hoping many of you have at least seen it. And that last line is an important one. That's what it's doing. It tries to give high inner products to word pairs occurring nearby and low inner product to random pairs of words. So these word embeddings have magical properties, which is what hooked me in this area some years ago. Like maybe you've seen many of these, like the cosine of the angle of these embeddings that you find. Capture human estimates of similarity, that lion and tiger have very similar embeddings, and coffee would have a very different embedding. Word analogies can be solved via linear algebra on word embeddings. So man is to woman, king is to, and turns out there's a man to woman or male-female direction such that these pairs of words are somewhat aligned, and linear algebra solves it. And this is very, very mysterious. The word vector space for different languages, like English and French, it's been discovered in the last year or two, can be meaningfully aligned via linear transformation. This is not something I'll address. It's something to think about as a consequence of the theory we're developing, but it's very intriguing that somehow there's some universal space which you can align across languages. So this is my way of just introducing these embedding ideas, and that they're magical. They train them, in this case, using this language task, like fill in the blanks kinds of task, and they have these magical properties. So they do well on some other task B. Here's another one that completely blew my mind. A very bizarre method for image embeddings. And these are these papers from the past couple years. Unsupervised representation learning by predicting the image rotation. So the idea is you're going to train a deep net, specifically a convolutional deep net, on the following task. So the input is an image, as well as its rotation by either 90 degrees, 180 degrees, or 270 degrees. Okay, and the desired output for this deep net is given this pair of images. Output, which of the three rotations was applied? 90 degrees, 180 degrees, or 270 degrees. So you train the deep net. So this is clearly just data you can generate yourself, image and its rotation. Train the deep net. You can have as much data as you like, right? Clearly. So the amazing thing is that the ConvNet trained on this self-labeled data learns representations of images that are quite powerful compared to the gold standard. That's what the papers show empirically. It completely blows my mind because this task seems trivial, right? If you tell me how to solve this task, I'll mentally apply a rotation to the second image and see, is it like 90 degrees, 180 degrees, or 270 degrees? And once I try those three things in my head, and it should just align completely at the pixel level. There's seemingly no reason to at all look at the semantic content of the image. But somehow, training the net, the convolutional net, to solve this task forces it to learn the representation. Any idea why? Any guesses? I mean, your guess is as good as mine. I'm going to suggest an answer, but. Yeah.
Well, intuitively reading descent doesn't prefer certain directions. So, like, if one method is to, as you say, like try to get it says just our rotation, maybe another way we could actually when the semantic content here sort of move in that average of these directions. Solve it.
No, I mean gradient descent would not have that property, that it's indifferent a priori.
I think that's what I mean, but maybe I'm confused.
Any other guesses? Yeah.
It's hard to express rotation with convolutions, right?
Exactly, yeah. So that's why the ConvNet was in red. The convolutional net is not a general purpose deep net. It is a very structured deep net. And it cannot express just any arbitrary operation on images. And so my algorithm, what I think is my algorithm, who knows, right? That I'm mentally rotating the image and then aligning it is probably not available to the convolutional net. It has to solve the problem in a different way. So this is a very graphic illustration of how representations can be learned by a seemingly bizarre and trivial method. It sort of makes you think, right? Like, what the heck is going on in here, right? How are we learning our representations? All right, and the third example, which is the one that will be most relevant. So that one, the previous one, I have no theory for. Okay, just this intuitive explanation. If you have a theory, like theory as in like rigorous mathematical theory, I'd be very interested. So the third one, and this is the kind of method we'll actually have the theory for. This we learned from a paper on sentence embeddings via quick thoughts. Is this the coffees?
Yes.
Oh, good, thank you. This is called sentence embedding. So just like word embeddings, right? Words can be represented by vectors. Here, you represent sentence by vectors. And there's been a lot of work on sentence embeddings, and this is the state of the art by Logeshwaran and Lee. And it's a word-to-vec-like algorithm for sentence embeddings. By the way, I should have said, the word-to-vec algorithm, people have applied it to anything you can imagine. Molecules, social networks, sentences, images, you name it. I think all possible bigrams or combinations of words have been explored with word-to-vec methods. So this is the sentence embedding version. So there are many ways you can have a word-to-vec-like algorithm. And this is something special. So it's trying to use, say, a deep architecture or some kind of architecture to map a sentence to a vector. And the objective is to minimize this kind of function, that the expectation over all pairs of sentences where you have x and x plus are adjacent sentences, and x minus is a random sentence from the corpus. So this objective should be minimized. And the expectation meaning you take pairs of adjacent sentences, add a random sentence, and compute this. Taking that expectation over triples of sentences. One pair is adjacent, and the third one in the triple is a random sentence. Now, I don't expect you to parse the objective, but turns out what it's saying is make adjacent sentences have high inner product, while random pairs of sentences have low inner product. And now you see why I call this like word-to-vec. Yeah, so I was talking to Philippe here, and he said he saw word-to-vec like, and he knew exactly what I mean. So this is like a well-known category of learners, word-to-vec like learners. Okay, so we call such methods contrastive learning, and in this case, for sentence embeddings, this is state of the art. For image embeddings, you can also do similar things. For instance, an early paper of Wang and Gupta used video. So you can imagine that two image frames that occur in the same video clip are semantically related. So they're embedding. So if you're learning an embedding for images, you want the images, sort of the images that appear in the same video clip to have high similarity, high inner product. So they've tried things like this, and it also works reasonably well for embeddings. Okay, so this is the main idea I want you to take away. So I gave you this survey of embedding methods, and the idea I want you to take away, the one that we'll analyze, is this idea. Like, why does this work? Make adjacent sentences of high inner product and random pair of sentences have low inner product. What does this have to do with task B later on? So I'm ready to go on, I believe, to the next section. So any questions on this section? Okay, so by the way, this sentence embeddings also capture human notions of similarity, and there are all kinds of amazing properties about this. For instance, in this case, the sentence, if I give you these 5 sentences and ask you to compare, find out the two most similar, all of you would say number 1 and number 4. And notice that they have no words in common. So the sentence similarity is somehow magical. Okay, there's no common words, so it's not just some kind of pattern matching. It's actually somehow understanding the meanings of words and composing them in some way to get a vector. Okay, so and again, training objective seems unrelated to the test objective, which is in the human heads, right? It wasn't trained on any kind of human any humanly labeled data about what sentences are similar. Yeah, and again, I have articles on convex on my blog about embeddings. So part 3, the new framework that I'll introduce in this talk. And it has various parts, which I'll describe to you now. So the contrastive, again, is this thing that, so what is contrastive? So remember I forgot to say this on the previous slide. This thing, right? Make adjacent sentences of high inner product and random pairs of sentences of low inner product. People's intuition about this is that sentences that are occurring next to each other are clearly related in some way. They're similar, right? Within the same paragraph, you're talking about basically similar things. So in that sense, these sentences are similar, and random pairs of sentences are dissimilar, right? That's the intuition people have why these objectives work, and that is indeed what we're trying to formalize, okay, in our framework. That you're learning representation by leveraging contrast between similar and dissimilar pairs of data points. Okay, so we call these contrastive. Okay, so we're trying to do data representation, and we're trying to do powerful data representation, so we want to solve them using linear classifiers, classification tasks using linear classifiers. That's the only setting I'm talking about. I mean, I'd start with the fully general task A, task B, but these are my task A and task B. I'm going to learn the representation by solving some task A, and task B is I'll be given some suite of classification tasks later on, and I'm going to try to solve them using a linear classifier on my representations. So part 1 of the theory is that there's, available data consists of these pairs, x, x plus of similar inputs, and random pairs of inputs, x, x minus, are treated as dissimilar. Okay, so somehow the algorithm that's learning the representation is learning from this kind of data. We call it contrastive data. Any questions? So from now on, we'll not worry about how this contrastive data was obtained. In my survey of embedding methods, I suggested how various ways you could do it, like for sentences, co-occurring sentences, images, clips from the same video, images from the same video clip, etc. But we won't worry about that from now on. How was this data obtained? Part 2 of this theory. We need a method to learn the best representation from some function class f. So function class meaning, think of it as a deep net architecture. It doesn't have to be a deep net, it can be anything. Think of it as a deep net architecture, for instance, ResNet 50 of a certain size. Okay, so that's the class f, capital F. So you want a method to use this kind of available data to train this architecture to produce representation f. And the objective will be something similar to what we've seen before. And the goal is to understand why minimizing this unsupervised loss, task A, helps for the supervised task later on, task B. That's the goal in the theory. I'm just laying out the elements of the theory, the formalization. Any questions? So the gold standard, of course, would be the headless, well-trained deep net on the same, in a similar domain. So if this data is images, and we are interested in classification tasks on images, the headless, well-trained deep net is, say, the deep net trained on ImageNet, like a vast data set of images. If it's language, it's trained on some language classification tasks, some large suite of language classification tasks. So you want, that would be the ideal theory, right? You somehow say, my method competes with that. That's the way people empirically test representations. Question is whether theory can say anything about it. That's going to be formalized. So I'm laying out so far, and in the next slide I will. So far I'm just laying out sort of the various actors in the theory. Yeah, so that's why similar is in italics. Any other questions? So far I've introduced you to the cast of characters. There's this available data. There's going to be we're going to fix a function class f. In that function class f, somehow we're going to learn a representation. And we want guarantees on the quality of this representation function. And if we are really ambitious and really lucky, maybe we'll compare to the headless well-trained net. So now part 3.1. So assumption about semantically similar pairs, which was the question. What does it mean that semantically similar pairs? Now clearly, there has to be some connection between semantic similarity and the downstream tasks. Nobody has made it precise, but intuitively there has to be something relating that. Otherwise, if that task was something completely unrelated, like this is images, and the task is something like use the image to predict the stock market, I mean, there's probably no connection, right? So somehow this similarity task must be somehow related to the task you are going to later solve, right? So the theory should try to make that precise and then give guarantees. And then once we make that precise, you all, or the people who work on this, can examine the assumptions and see if they're reasonable and so on. So that's what I'm going to do. So this is the assumption about semantically, our formalization of what we think people mean by semantic similarity. And it's very minimal assumption. So the assumption is that the world contains a collection of classes. Could be continuum, infinite, finite, whatever. We are agnostic. So there are classes of objects. So there's some collection of classes. So in this case, yeah, you see these classes, animals, and various types of trees, and means of transportation, etc. Now, you can, so what are semantically similar pairs? So nature picks, so when they present as a similar pair, they pick a class from this sea of classes, according to this measure, which we don't know. So C1. And now, and each class has some measure, rho of C, associated with it, which nature knows. And now when it gives us a semantically similar pair, it's going to draw two samples from that class, C1 and C2. Sorry, not C1. X and X plus from that class, not C1. X and X plus from that class. And the dissimilar pairs involve drawing two different classes independently and drawing a sample from each. Okay, so it sort of makes sense, right? That in the images, in the image domain, yeah, this makes sense. In the text domain, you would imagine that, yeah, within the same paragraph thing, the sentences are talking roughly about a similar thing. So that's a class, some small class of things you could talk about. So that's a formalization of similar and dissimilar pairs. That nature has some set of classes, arbitrary, any kind of overlap is allowed, and it's drawing similar pairs by picking one class and picking two samples from it, dissimilar pairs by picking two classes and drawing a sample from each. Questions? I can come back to this slide. And by the way, this is reminiscent of co-training and multi-view assumptions for the small group of you who might know about those buzzwords. All right, so that I'm just restating that in text. I already gave you the picture. Okay? All right. The next piece of theory. What downstream classification tasks are of interest? Well, nature had a set of classes of objects. And now nature picks a random pair of distinct classes according to the joint measure. And now it picks K1 samples from the first class, K2 samples from the other class, and asks you to solve the binary, labels them. This is class 1, this is class 2, and asks you to solve that binary classification task. Okay, so that's the downstream task. And so the evaluation of the representation is that nature picks a random binary task as above. We can extend this to k-way tasks. And your representation will be evaluated by using that representation as the input to a simple linear classifier, a logistic classifier on the representations. Okay, so the supervised task has this logistic loss on the pair of classes that nature has picked. And you're taking the expectation over all pairs of classes. So your performance is the average over all pairs of classes. Just as an aside, in case you don't know, logistic classifier for a binary task is something like this. Data is labeled as binary, 0, 1. And these are the data points. And the logistic classifier trains two vectors, W1 and W2, one for each class. And for any data point, the probability that your label is 1 for the data point is proportional to the exponential of W1 inner product with X and the sum of the two exponentials. And the probability that this classifier labels it 2 is 1 minus that probability. It's called the logistic classifier, also called softmax, the usual top layer of a deep net. Okay. So I'll rewind the slides so you can see all the things, all the elements. But that's okay. So just quickly, let me just do this fourth part too. And our method to learn representations is just like the quick thought objective I said earlier. It's just the same objective, except there we were saying, okay, similar pairs are adjacent sentences. So now we don't care adjacent or non-adjacent. We're just given similar pairs, dissimilar pairs, and the quick thought objective. So similar pairs, on average, should get high inner product, vectors with high inner product, and dissimilar pairs should have low inner product. And of course, that's a population version, like over the entire population of examples. Empirically, in machine learning, of course, you have a finite sample, and you're going to train it using a finite sample. And I'm going to assume that unlabeled data is cheap. So I assume that the number of training samples is unlabeled data, right? Just similar, dissimilar pairs. And whoops, what happened here? Yeah. Whoops, yeah. So assume this amount of unlabeled data is large enough so that the empirical objective and the unsupervised loss over the population, they have roughly the same value. And so they are about the same. Okay, that's an assumption. Important part, nobody knows how to prove the convergence of training on a 50-layer deep net as of now. So in this theory, we are not going to say this method works in polynomial time or quadratic time or whatever. There's no such theory currently. So we are ignoring the computational cost of minimizing the unsupervised loss. We're just giving guarantees on this loss, assuming you could optimize it. So I'll rewind and walk you through the theory again, and you can ask me questions. So yeah, we were given this similarity data. We fixed some function class like ResNet50, and the important key assumption is the assumption about what semantically similar pairs are. And there we were assuming that nature has a set of classes out there, which we don't know. And similar data is generated according to this process. Nature picks a class and gives you two samples from it. Those are similar data points. Or two different classes, and that's dissimilar data points. Okay, that's our assumption. And this is connected to the downstream task, as nature will pick from the same sea of classes with the same measure and ask you to do a binary classification task or k-way classification task using data from those k classes. Okay, so that's the downstream classification task. And and in this framework, what I described here, you're training a logistic classifier, a linear classifier with a logistic loss to solve the downstream task. Now, and these log and so on appearing in this training objectives are actually related, okay, in the unsupervised and supervised. This was also not clear earlier, like why, people have like these various information theory ways of understanding things or whatever, where the logs come from, et cetera, et cetera. We had some paper too trying to explain the log. But in this theory, the log is just related to the logistic loss that you use in the downstream task. That's all. There's no mystery. Any questions about the framework? Yes?
Is this approach related to an approach where we just regard the dissimilar and similar pairs as distorted labels for metric learning or equivalence relation learning?
It's not the same because there's no metric on the classes. There's only an embedding of the data point.
Equivalence relation.
Discrete metric among points or among classes?
Among classes,
Yeah, so we're not assuming anything. Yeah. And the other important thing is that there could be a sea of classes, infinitely many classes. So yes, you get pairs of data from the same class, but you may never repeat a class. So you cannot treat this as a labeled classification problem. Yeah. Which your question anyway, I think, understands that, yeah, it's more like metric learning. Yeah, so in the paper we sort of do a careful comparison with all the ideas out there. We believe this is new. Other questions? Okay, so warm up, a simple result. So remember, we're trying to prove some bounds or some guarantees on this classification loss. And the first simple result is that if the unsupervised loss is low, somehow your unsupervised training seems to succeed and you get low loss, then celebrate, because the average loss on the classification task is going to be low. It's a very simple theorem. Ignore this tau, which is the collision probability for a pair of random classes. So, if the number of classes is large, you never, if you pick two random classes, they'll never be the same class. So that's all tau is. So that's usually small. So basically, that's the result. Tau, think of tau as small. So this is useful since often the unsupervised loss is low. And the key step in this is just Jensen's inequality. That, I didn't do the mean classifier. What happened to the mean classifier? I think I'm missing a slide. Okay, so sorry, I'm missing a slide. The mean classifier is the classifier where if you have two classes, you take the representations of all the points in this class, treat that as one vector, take the representation of all these points, treat it as the other vector, and use that vector as the solution to the logistic regression, the two vectors in two classes. Remember that in logistic regression. Oh, I do have mean classifier, sorry. So mean classifier, I do have, yeah. So instead of training the logistic loss, we just said W1 to be the average representation for points in the first class that you're given in the sample, and mu2 or W2 to be the average in the second class. Okay, and then evaluate the logistic loss. So that's a mean classifier, the mean logistic classifier. And clearly, the performance of the best logistic classifier is at least as good as the mean classifier. So this is just using the analysis, the mean classifier. So the warm-up is that that if the unsupervised loss is small, then the supervised loss is small, and you prove it using this mean classifier on the left-hand side, and Jensen's inequality, which if you know, implies basically that when you replace the expectation within each class by the mean, there's an inequality, and that's Jensen's inequality. Okay, so it's a fairly simple result. So this is already useful, but somehow, sometimes it's not. Oh, by the way, this also, the detailed analysis shows that the number of labeled samples needed will be the sample complexity of linear classification. And in fact, I'll show you results later on, which shows that actually, even if you have 5 labeled samples per class, you do very well in many settings. So really, the advantage of learning the representation function is that in the downstream task, you need very few labeled examples. And that can be made precise in this theory. The other comment is that this arbitrary looking choices in the unsupervised objective, which I mentioned earlier, log, etc. And people have sort of struggled to interpret that, like, is it information theory? What is it? Turns out has a simple interpretation. It's related to the loss function using the downstream classification task that you're going to use it for. And if the downstream classification task uses some other loss, not logistic, but hinge loss or something else, it'll show up in the unsupervised loss. That's it. There's no, at least in this theory, there's no mystery about where the log comes from. Okay, log and the exponential. Okay, and so that was a simple warm-up. There's a more detailed analysis, which starts getting hairy. So I'm out of time or running out of time, so I won't go too much into that. But there's a more detailed analysis of the right-hand side when the unsupervised loss is not small, but you can still analyze that using some notion of variance, geometric concentration among the representations within class, and there are some quantities, new quantities we define in this theory, using which you can analyze this. And this guarantee is strong if we have some kind of a contrastive F, which has a property that it's very concentrated within classes and quite different between different classes. So if you have that, then you get some kind of guarantee. Empirically, we do find representation are pretty concentrated in our experiments. So let's go to the dream result that I seem to promise at the start. So the dream result would have been you do representation learning, and at the end of it, you're as good as the best supervised model in the class. Okay, compete with the best representation. So the performance of your classifier, the F hat, which is what you came up with, your representation, which you came up with, the supervised loss on that, is at most some alpha is small, times the supervised loss of the best classifier. In other words, for example, the headless, well-trained deep net. That would be like the dream result for this theory. Okay, so I started with this dream goal. The second term generalization error is something that depends on the amount of unlabeled data, which goes to 0. So this would be the dream result. Okay? Any questions? So, well, easy theorem. This is impossible for an arbitrary class of functions and arbitrary tasks. So that's one of the advantages of a theoretical formulation, that you can start saying what's impossible. And so this thing that people have been, like the El Dorado or whatever, that people have been after, is in full generality not possible, even in this model, in this framework. And that's why the theory has to work around it. So what the theory I showed you was our way of dealing with this impossibility results. So how do you still get some guarantees? Questions? So finally, yeah, there's some progress towards the dream result. You make fairly strong assumptions about the concentration behavior of representations. Like within a class, they're concentrated kind of like sub-Gaussian, for those of you who know that. Then you can start proving much stronger bounds. Okay, and then you can start competing with the headless, well-trained net. Okay, under that assumption, which I won't talk about much. So any questions about this theory? And then I'll move on to the conclusions and finish. Who had a question? You're pointing to somebody. Oh yeah, please. Yeah.
Intuitively, why is the thing you said is possible impossible?
Because we are sort of not assuming anything about the class of functions. So if you're not going to make any assumptions about that, then there's a simple counterexample. I'm not just even saying it's NP hard or anything. It's just impossible. It's a simple example in the paper. Yeah. Any other questions? Yeah.
You figure out things that are similar if you don't have classes right now.
So remember, the empirical methods work. And the empirical methods have all kinds of heuristic ways of finding similar things, like sentences that are co-occurring, images that occur in the same video clip, etc. We're agnostic about that, like in practice how you find similar pairs. But in our theory, similar pairs correspond to nature having this sea of classes and picking a class and giving us 2 samples from it. That's what our theory is assuming. Empirically, people have all kinds of ways of identifying similar things. Did I answer your question?
What nature's classes are.
No, we don't know. That's the whole point. This is like ansatz about what's going on, like some assumption about what's going on in the background, which we don't see. So the Bayesian alternative would be to have a full ansatz about what nature is doing. And this is a very minimalistic assumption about nature. Any other questions? Yes?
Not even in full generality, like in the real world, there would be like a hierarchy of classes.
Correct. Yeah, that's
So-
going to be my own problem. Yeah. Yeah. Okay, any other questions before I move on to conclusions? Okay, so yeah, as I said, yeah, there's some dream results which I've just briefly sketched. Extensions, there's an extension to K-way classification, as I said. And the corresponding unsupervised objective also changes. So, this is the kind of thing, like people just try various objectives for unsupervised learning. And there's like no theory to guide, like what exactly are you doing? Like y log, y exponential, the functional form. And, it becomes clear that if you are interested finally in evaluating on K-way classification tasks, you need a different objective. And we give that in the paper and analyze it. And there's a new unsupervised objective based upon blocks of R similar data points. So remember that for sentence embeddings, we said, okay, 2 sentences that appear in the same paragraph are similar. Well, there are 5 sentences in the paragraph. Can you leverage that? Well, we give an objective that leverages it, and actually empirically it helps, etc. Okay, so that's the advantage of a theory. I hope I'm trying to convince you that that's why you do theory. Like, it gives you these insights which possibly would take a lot of trial and error to come up with. Okay, so some quick experiments. So as I said, these methods already work, right? I tried to give you a survey of that. So the experiments are basically illustrating the theory. And so here's a database which we created, Wiki 3029, where we took 3029 articles. I have no idea why my students took 3029. And from each article, 200 sentences. So those are the classes that we are assuming nature is drawing from. And now nature is going to give us pairs of sentences from the same class from the same article that's similar sentences, etc. And we train the sentence representations using the objective. And then there are some held out two-way tasks, right? So you hold out some pair of articles or 10 articles, etc. And you're going to now do the two-way classification task on those articles. Given a sentence, it come from this article or that article. And you're given a little bit of labeled data or 10-way classification task. And so what you find here, I've suppressed the second line, which is somewhat distracting. So the first two lines is just, the average performance on binary tasks and 10-way tasks. The first line is binary, second is 10-way. On the left-hand side, you have supervised. On the right-hand side, you have unsupervised. TR is trained classifier. Mu is this mean classifier. And mu5 is like just mean of 5 labeled examples. So you're just given 5 labeled examples. And even with 5 labeled examples, actually, you do pretty well. So you have basically 10 labeled examples, okay? 5 from each class in a binary classification. So after you've learned the representation, you just need 5 examples from the article to be able to classify pretty well. And you can see that in this case, the representations learn, the headless well-trained deep net. It's not a very deep net, there's 2 or 3 layers. And the unsupervised representations actually are pretty similar. Okay. So here, yeah, I'm again emphasizing just 10 labeled examples total, and you can already do pretty well, almost as well as the supervised model. For CFAR 100, which is an image data set, 100 classes and 1,000 examples of each. Is that 1,500, something like that? Here, the supervised unsupervised gap is somewhat larger, but still the unsupervised classifiers, the unsupervised representations are doing pretty well. The classifier using even like 5 examples is actually not bad. Okay. And as I said, the analysis suggested these new objectives, like if you have a paragraph with 5 sentences, that's like 5 similar things, not just 2 similar things. You can extend the theory and leverage it. And in the standard, the state-of-the-art quick thought, you improve it by using this new objective. So by a few percentage points, which is not trivial in NLP settings. 2-3% is quite significant. Just by a simple change in the theory and analysis, you come with a newer objective which improves the sentence embeddings, state-of-the-art sentence embeddings on some downstream tasks. Okay, so I'll conclude. I've given you a first cut theory for formalization of representation learning with very minimalistic assumptions. Future work would be extensions to more intricate settings, which was asked earlier. For instance, we made no assumptions about what classes nature has, but clearly in practice, objects have some hierarchical semantics, like big classes, subclasses, etc. It would be great to have a theory to leverage that. I encourage you to think about it. We haven't thought very hard about it, so it may well be not so difficult. More empirical and theoretical development. I think these are all related, like this solving task A, task B. There are many buzzwords: meta learning, learning to learn, transfer learning, etc. And I think similar ideas should be useful in all of those. Thank you very much, and there are various resources. Thanks.